name is Wyatt Wolf, and I'll be introducing our senior design project on the electrical chemical conversion of carbon dioxide to methanol. To begin, this project is driven by the rising atmospheric concentrations of carbon dioxide, a major greenhouse gas contributing to environmental challenges. As the need for sustainable carbon utilization technology grows, our team has focused on developing solutions to address this issue. Specifically, we aim to design and optimize a membrane electrode assembly electrochemical flow cell. Our goal was to implement flow paths and catalysts that enhance carbon dioxide reduction, improve methanol selectivity, and maximize overall reaction efficiency. With these objectives in mind, the team got to work. Over the academic year, our work was divided into two major phases, fall and spring semester. In the fall, we focused on determining the reactor configuration, modeling the system, and manufacturing the necessary components. By the end of the semester, we had conducted an in-depth literature review, designed our model through the rapid prototype lab, developed a test matrix, ordered all required parts, and assembled a fully functional reactor. Moving into the spring semester, we began by ensuring the reactor was operational. Once confirmed, we proceeded with the planned test matrix, applying catalysts and conducting experiments. After completing our tests, we analyzed the data collected in lab. Finally, we will conclude our project by presenting our findings at E-Days and to Caterpillar. Now that we have covered the big picture, let's dive into the details. Our team synthesis tree guided us through key design decisions, starting with choosing a membrane electrode assembly over solid electrode devices. MEAs offer better ion transport, reduce ohmic losses, and improve catalyst utilization, making them more efficient for electrochemical CO2 reduction. Next, we opted for a passively mixed microflow pathway to enhance mass transport without requiring additional energy input, improving reactant distribution across the catalyst surface. Finally, we selected an aqueous flow system to facilitate ion movement, maintain stable reaction conditions, and simplify system integration. These choices collectively optimize methanol production efficiency while also maintaining a practical design.
Hi everyone, my name is Angelica and I'm going to go over the chemical mechanisms that we want to see in our reactor. So first, we apply a voltage to our catalyst. Hopefully it's negative enough to grab that carbon and reduce that whole oxygen off, and then we further reduce it with hydrogen ions in order to get our desired product, methanol.
Hi, I'm Allie, and here is our block flow diagram. As you can see, it's kind of broken up into three separate components. First, we have our cathode side, then the membrane, and our anode. On the cathode side, we have humidified CO2 flowing through along with an electrolyte flow, and then our anode side, we just have that electrolyte flow flowing through. On the membrane, it's a bipolar membrane which allows hydrogen ions to pass through to the cathode side. To get a better look at this, we're going to put together our reactor step by step. So first, we're going to start with the end plate, instantly followed by the nickel foam, and then our first KOH compartment. Now this makes up the anode side, then the bipolar membrane, followed by another KOH flow compartment, followed by a gasket, followed by the carbon cloth, which has the catalyst sprayed on, which the catalyst faces the bipolar membrane. This is then followed by another gasket, and lastly, our flow field is placed on top, which makes our anode or cathode side and altogether our reactor.
Throughout the process of obtaining the reactor and moving forward into testing, the team ran into a lot of challenges. One of which was gas leaking from the tubing. Another was improper tightening of the system overall would cause the carbon paper that holds the catalyst to break and skew the data. Also, the team was unable to supply enough voltage to the system. In order to remedy a lot of these issues, the team made some acquisitions to further optimize the process, one of which was pressure fittings for the tubes. Another was a digital torque wrench that helped to more accurately determine how much pressure the system was applying. The team also switched from a carbon paper to a carbon cloth, which is more flexible and pliable and less likely to break. The final addition that the team made was getting a voltage booster that was able to supply more power to the system over time.
So the team actually ran a few tests with two different catalysts with the remaining weeks left of the semester. The first one we ran is called a cyclic voltammetry, or CV. A CV tells us two important things. One, it tells us about electrode surface properties. So a CV responds to changes based on electrode surface conditions. So therefore, a consistent reproducible CV is actually considered clean. So we want to run this multiple times to make sure it's running the same pattern every single time with very little noise. It also tells us about reduction behavior. CVs tell us whether a species undergoes oxidation where it loses electrons or reduction where it gains electrons, and at what cell potential these occur at. Here are two CVs for the two different catalysts the team ran this semester, where total voltage speed on the X and current density is on the Y axis. I want to point out two major things. First, our reduction peaks. This shows us that reduction is happening on our catalyst surface, and therefore some sort of carbon dioxide reduction is taking place. Additionally, those downward slopes towards the -5 volts, we see a consistent slope showing that there is oxidation happening within our reactor. Overall, these CVs were both very clean, and we can prove that reduction is happening here. Which moves us into long-term testing. The long-term testing that we decided to run is called a chronopotentiometry, or CP. So it tells us a few important things as well. First, catalyst stabilization. A good, stable catalyst should be able to hold a constant current density at a constant voltage over time. Therefore, our graph should look like a straight line theoretically. It also tells us about the time needed to reach steady state. So once a curve converges to a certain point and stays there, it shows us when and at what cell potential is needed for the reactor to hold that same current density. So going into comparing both of our catalysts, they were run at the same current density for 7 hours, and as you can see, Catalyst 1 has the best steady state curve, whereas Catalyst 2 shows the signs of mass transfer phenomena happening, or maybe some blocking, something like that.
As we've mentioned, sustainability is really at the core of what we're doing, with the goal that in the future, CO2 capture research and reactors like ours can work together to reduce greenhouse gases while also generating alternative fuels. To assess the sustainability of our project, the team used the ALKI 7 sustainability indices and gave our project an overall sustainability rating of 5.3 out of 7. Now, to get into some of the specific numbers, the highest rating we gave was for innovation, which was rated a 7 out of 7. This reflects the novelty and ongoing development of CO2 to methanol conversion technology. However, there is still plenty of room for improvement in other categories, especially when we think about scaling up in the future. For example, one area that needs work is the value chain management, where we rated ourselves a 4 out of 7. This is largely due to the limitations we've faced with supplier and material sourcing, mainly due to time constraints in our current network. If we were to scale up to industrial level, we would need to develop stronger supplier connections, which would help reduce costs and streamline the sourcing process.
If our electrochemical reactor were to be scaled up, safety risks become more pronounced, particularly in areas such as piping and tubing failure, reactor part damage, and hazardous material exposure. Piping failures at higher operational pressures could lead to leaks or bursts, creating safety and environmental risks. Damaged reactor components may compromise system integrity, potentially causing inefficiencies or hazardous conditions. Additionally, contact with potassium hydroxide presents a chemical burn hazard, requiring strict handling protocols. Slippery conditions from spills and flammability of alcohol products also increase risks in a large-scale setting. Addressing these hazards through robust material selection, containment strategies, and proper safety protocols is essential for assuring a safe and scalable process.
With the safety of scaled-up process in mind, the team created a predictive process and instrumentation diagram shown here. This shows a process control diagram for an electrochemical system with a cathode and anode chambers separated by a bipolar membrane. And that includes catholyte and analyte tanks, pH controllers, flow controllers, pressure controllers, and a power supply connected to a voltage controller.
Going into the market and competitive analysis, the team decided to break it up into two main sections, one for the MEA, or the membrane electrode assembly, and then another for green methanol production. Looking at the MEA, the market currently sits at $135 million. Compounding over the next 8 years at about 22% would bring it to $872 million. And a lot of the growth factors for this exist around sustainable energy sources and just sustainability in general being a focus. Moving into the green methanol production, currently the market sits at about $351 million, compounding at 53% over the next 8 to 10 years, and is projected to be $16 billion by 2032. A lot of the growth factors for this are very similar in terms of sustainable fuel use, but also an increasing use in electronics. Looking at the team's budget, the team had $40,000 to work with given to us by Caterpillar. We broke that down into three main sections. We have the actual fabrication of the reactor, the tools and the accessories that we needed in order to perform a lot of our testing, and then as well as a trip to present to the Caterpillar sponsors and executives. Going into the techno-economics, we see our 5-year projected economics analysis. The team calculated about a negative 22% ROI for the scaled-up process, which would increase the debt over the next 5 years to almost $2.5 million.
This emphasizes the lack of feasibility for scaling up the process currently and proves that the focus going forward should be on optimization of the reactor, the process, and also proof of concept.
To wrap things up, our team successfully designed and optimized a membrane electrode assembly, or MEA, that demonstrated promising performance in reducing carbon dioxide. Through this work, we've been able to highlight the real potential of CO2 reduction as a tool for broader carbon utilization, especially as industries look for more sustainable solutions. Along the way, we've identified several key parameters that directly impact reactor efficiency, from catalyst behavior to system design, and applied both chemical and biological engineering principles to tackle a real-world sustainability challenge. Looking ahead, there are several promising directions for continued development. On the reactor and reaction side, future work could focus on exploring new catalyst materials, refining electrolyte characteristics, and implementing separation methods to improve product purity and recovery. For scalability, efforts might include removing the heavy metal end plates to reduce cost and weight, increasing production rates, and evaluating whether scale-up or scale-out approaches are more effective for practical implementation. Thank you for watching, and I hope this presentation offered valuable insight into the potential of electrochemical carbon utilization.